So our next problem involves a meteor with mass m approaching a planet of mass capital M and radius capital R from the edge of the universe. And an important note is that capital M, the mass of the planet, is much larger than lowercase m, the mass of the meteor. So also one other thing to touch on just before we get into the calculation parts is this edge of the universe part. Well, remember how we defined gravitational potential energy. Gravitational potential energy at an infinite distance away from an object is defined as 0. And so that's basically because, mathematically speaking, we're dividing by infinity. The radius is infinity. The distance away is infinity. And so this is basically saying that our initial potential energy is 0. That seems kind of weird because it's like, oh, 0 potential energy, that's like, you know, dropping this pen off there, there's 0 potential energy relative to this stand. However, potential energy only goes negative from there, and it's the change in potential energy that matters. So, also, another important note is this capital M versus lowercase m. Consider me jumping off of the planet, of the Earth. You know, when I jump, momentum is conserved. I go up, therefore the planet must go down. However, Earth is so much larger than myself that it almost doesn't move at all. Similarly, when this planet exerts a force of gravity on, or when this meteor, exerts gravity on the planet almost doesn't move at all because it's so much larger. So that's an important thing to remember for this problem. So, part A, calculate the kinetic energy of the meteor when it is a distance d away from the planet. And part B is, with what kinetic energy and velocity v does the meteor collide with the planet, assuming there is no atmosphere, meaning no air resistance or no energy loss. So, part A. Energy. Conservation of energy, right? So, initial potential plus initial kinetic goes to final potential plus final kinetic. Now, this is kind of how we see potential energy and 0 energy at an infinite distance away, where it's g times the mass divided by the distance away. However, the distance is infinity. So anything divided by infinity is 0. Plus initial kinetic, well, it isn't moving up to begin with, equals final potential, and remember it's negative, plus the kinetic energy. Solving for kinetic energy, we get that is equal to g times the little mass times the big mass divided by d. Moving on to our next part. What is the kinetic energy and the velocity of the meteor when the two collide? Energy, so potential plus kinetic equals potential plus kinetic. Well, gravity is a conservative force, therefore it doesn't matter where we start. If we start at the very beginning of the problem where it's an infinite distance away, or if we start when it's that distance d away, it's still the same amount of energy between the final end, or between its initial state and at the collision. So it's just easier, there's less to write when we say that it's a distance of infinity away at the edge of the universe. So we start with this potential energy of 0 plus 0 kinetic energy going to this gravitational potential energy now at a distance r away plus this kinetic energy. And we get the kinetic energy is g times m divided by r. Now, for the velocity, well, we know that kinetic energy is equal to 1/2 mv squared in the general case. So let's plug in with what we already know, that kinetic energy of the meteor is also equal to g times m divided by r. Solving for v, we get that v is equal to the square root of 2 times g times capital M, remember because the mass of the meteors cancel out, divided by r.